For today's lecture, what we're going to do is we're going to generate what's called symmetry-adapted linear combinations of atomic orbitals. And so, symmetry-adapted linear symmetry-adapted linear combinations of atomic orbitals. For short, these are represented as SELCs, the acronym. And what this does is it allows you to look at and see what ligand orbitals will interact with what central atom orbitals. And so this is useful for transition metal compounds where you've got octahedral or tetrahedral symmetry. You can do this for all different types of atomic orbitals, sp, d, even f, which we're not going to worry about. But we'll start with a simple example and then get in maybe something a little more complicated. And so let's pick a molecule where this can be illustrated in a relatively reasonable sense. And we'll use this one, ethene. And so what we've got to do first, before anything else, is identify the point group of this. Now I've already gone through all these kinds of things. And so you can find that the symmetry of this molecule is D2H. Now reproducing from the character table for this in the back of your book, what symmetry elements do we have? We have the identity, of course. 3 different C2 axes. Those do not belong to the same class. They are unique symmetry elements. And then we also have an inversion center, I, and 3 reflection planes, now if you look at the character table on the back of your book, that's on page 663, there are Cartesian coordinates attached to these. This C2 axis is Z, that one's Y, that one's X. The 3 reflection planes are XY, YZ, and XZ. Sorry, I got those backwards. Now, it actually doesn't matter if you reverse the order on those. What does matter is when you set up your Cartesian coordinate system, that you do it consistently. Okay? And so, what we're going to do is define our Cartesian axes. And so if you see this happening, like you would see also in C2V, you have to specify which axis is which one. And so we're going to have the z-axis, which is the vertical one, actually coming in and out of the plane of the board for us. And then we can define the x and y axes. Okay, and so let's just do that. Like this, like that. Up and down one is y, left and right is x. It doesn't actually matter how you do that. You can reverse what I did here. You'll get a different result in the character table when you do the next step that we're going to do. But at the end, you'll still get the same result. So that's up to you. But once you define, you have to be consistent. And z-axis has always got to be the vertical one, the principal axis. Okay, so what we're going to do next is we're going to generate a gamma reducible. And this is almost exactly the same thing as we did for the vibrational analysis before. The difference here being we're considering not the number of unmoved stretching vectors like for a carbonyl or whatever, but the number of unmoved atoms in the molecule. So, let's look at that. Okay, we've got 1, 2, 3, 4 hydrogen atoms in our molecule. If I do nothing to my molecule at all, how many hydrogen atoms remain fixed? Answer, all. And so, the character underneath there is going to be 4. Now, it turns out, because this is a weird molecule to pick actually for this, right? If we rotate about the z-axis, which is coming right through here, right through the middle of that double bond out at you, and behind the board too, of course, you're flipping the molecule over. And so if you want to see what happens with that, if we go hydrogen 1, hydrogen 2, hydrogen 3, hydrogen 4. Right, when I'm done flipping along the z-axis, what you'll find is that this is hydrogen 1. Hydrogen 2 is where 4 was. Hydrogen 3 is over here. And hydrogen is 4 is over there. So that is the C2Z rotation. To make a long story short, what happens is all of the hydrogen atoms move. None of them stay fixed, and the character for that operation is 0. Okay. The other axes are going to look something like this. So transposing that on top of there. And you can see probably pretty clearly from that as well. If I rotate about X, I flip the molecule over that way. Hydrogens 2 and 3 and 1 and 4 exchange, and therefore everybody moves. Again, nobody stays put. And if I flip the molecule over like this, hydrogens 2 and 1 and 3 and 4 exchange, and so the character for that operation is also 0. Now the inversion center is right at the confluence, if you will, of the 3 Cartesian axes. In fact, with an inversion center, what you're going to find is almost always everything, unless the inversion center is a central atom and you're considering the central atom, everything is going to move. So, character for that is also 0. Now, here's where it depends where your coordinates were defined. Right? The xy plane is a horizontal mirror plane, because if the z-axis is right here, and that's the vertical axis, the plane of the board is the horizontal plane. The horizontal plane contains both carbon atoms and, more importantly, all 4 hydrogen atoms. And so all 4 hydrogen atoms remain the same. Now, one of the things to note about this is because the atoms are what they are, and they're hydrogens, that character is 4. If we start considering things that have p orbitals when we do the next step, there could be negative signs involved. But if we use the XZ plane, which is this one coming out of the board at you, parallel to the ground, that reflects everything. And likewise, so does this plane here. Okay. So we've generated our gamma reducible. Now the next step is to reduce it. And so now we're proceeding exactly as we did with the vibrational analysis. So the first thing we have to ascertain is the order of the group, which is the total number of symmetry elements in the group. We have 1, 2, 3, 4, 5, 6, 7, 8. So the order of the group is 8. Some books actually say that right in the character table, some don't. Yours is one of the ones that doesn't, so you have to count them up. But there are 8 elements, right? So now we're going to reduce our reducible. And so what you're going to do is test each symmetry against gamma r to see how many times each symmetry contributes. Now if you look at your character table, they're all singly degenerate. Some are A's, some are B's. We have Garada, which is the G, and the Ungarada, which is the U. What that means is, again, that it's either symmetric Garada or anti-symmetric Ungarada with the inversion center. And so more on that later on. So let's test the first one, which is AG. So remember how this goes. You're going to take 1 over the order of the group and then multiply it by all of the individual elements that go here. Now if you look at your character table there, all the way across that row are positive 1, as there always will be for the totally symmetric operation, which in this particular point group AG happens to be. Now the nice part about this is we get off pretty easy here. You only have 2 things you're going to have to worry about. What happens with E and what happens with the XY plane, because the characters here are all 0. And so you're going to be multiplying by 0. For example, if you're considering any of the C2 axes. So all we have to do is look at, on our character table, in A1, or AG rather, this column and this column. Okay? And so, what we have is, remember, you do have to worry about what's in front of this. Now, these are all unique, but if there's a 2 or something, you have to multiply by that. So we have 1 times 4 times 1. Everything else is going to be 0 until we get here. And again, we have 1 times 4 times 1. Therefore, AG contributes 1 time to the gamma reducible. Now we're going to go and do the same thing for all the other symmetries along the character table. So the next one is B, 1G. Under the identity, we have a 1, and we don't worry about the next 4 things. And under the XY plane, we also have a 1. And so the contribution is effectively the same as the last one. So we're going to have an orbital that is B1G as well. Next up, B2G. Have a 1 here, and what do we have under XY? A negative 1. So, the contribution here will be 1/8 times 1 times 4, 1 times 4 times 1, plus 1 times 4 times negative 1. 4 minus 4. 0. So no contribution from that one at all. Next. Oops. Nope. B2G. We have, at least in terms of the characters that are of interest, 1 and negative 1. So again, when we multiply that out, no contribution. So you get the idea here. The ones that will contribute, so you can speed this up a bit if you're comfortable doing it. The only ones that are going to contribute are the ones where, since this is always going to be a positive 1 here, the ones that have a positive 1 there. So I won't do that, but just look at that when we're done, and you'll see that that's actually the case. The next one is B3G. A 1 here, and what do we have under sigma xy? Another negative 1. So again, that's going to be 0. The fifth element that we have is AU. With a character of 1 here and a character of negative 1 there. So again, we're going to go 1 times 4 times 1, which is 4. 1 times 4 times negative 1, that's 0. And so the contribution of AU is 0. Next one down. B1U. Again, a 1 and a negative 1. So we're going to get 4 minus 4 yet again. And the contribution of AB1U, contribution is 0. Next, B2U. Now, you have a positive 1 under sigma xy. And so, the contribution of AB2U for that symmetry is going to be 1 times 4 times 1 all that times 1/8 is 1. So that contributes. So we've got 3 of our 4 things we need, and when we get to B3U, and that's got that positive integer there, and so the contribution of B3U is 1/8 times 1 times 4 times 1, or 1 times 4 times 1, which is 1. And so now, we have our gamma reducible. So remember what would happen here is that if I added up the characters for all of these, I would get 4, 0, 0, 0, 0, 4, 0, 0. Because the number under the identity for this gamma reducible is 4, we have to have 4 singly degenerate contributions to it. We do. So now we have our reducible representation. Reduced. So let's get that off of there. Mac went to sleep. What do we do next? Next we do the generation of the cells themselves. And the method for that is called the projection operator method. And so what this entails is looking at one of the 4 hydrogen 1s orbitals on hydrogen and seeing what they transform into under the symmetry operations of our group. So let's do that. Like so. Imagine the 1s orbital on this hydrogen. Let's select it, and you only have to do this one time if everything is singly degenerate, which it is, which is nice. You only have to do this one time to generate the first part of the projection operation. So let's put sigma 1 here. You could equally write H1 if you like, but since we're talking about the orbitals, I'll represent it this way. What happens if I do nothing to my molecule? Where does sigma 1 end up? Well, it ends up where sigma 1 originally was. So the identity turns sigma 1 into sigma 1. Now, what happens if I rotate about the z-axis? Remember, that's the one coming out of here. It's twofold, so it's 180 degrees. And so we're going to go all the way over to here. Right? So hydrogen 1 and hydrogen 3 change places. Likewise, sigma 1 and sigma 3 change places. So after that operation is complete, sigma 1 has transformed to sigma 3. For the y-axis, I flip the molecule over like this. Hydrogens 1 and 2 are going to change sides, and therefore sigma 1 will transform to sigma 2. For the x-axis, I flip the molecule over this way. Sigma 1 is going to transform to sigma 4. X-axis goes through here in the plane of the board. I exchange hydrogens 1 and 4 and 2 and 3. So that's why sigma 1 and sigma 4 are exchanged. The inversion center. Remember where that is. That's right here. And so if I do the inversion, I translate sigma 1 to sigma 3. Like that. Now, the planes. This is why you have to keep your Cartesian coordinates straight. Because if you all of a sudden decided you were going to change what they were, this would no longer be valid. You would have different contributions from other things. So this is arbitrary as well. You could have a different representation if you pick different Cartesian coordinates. So try that. If you want to do it, you can exchange x and y. You have b 1u in there. Or one of the other symmetries. Alright, so xy is the plane of the board. This hydrogen is in the plane of the board, and therefore that remains sigma 1. Alright? If this were a p orbital, what would happen is when you reflect there, the p orbital stays in place, but the sign of the wave function flips. You have a negative sign there. We haven't done that yet, but I will show you an example where we do. Okay. For sigma xz, this plane here, parallel to the ground, 1 and 4 exchange. And in yz, this one, 1 and 2 exchange. And so that's the projection operator method. First part. You have to find out how these orbitals change around. How one transforms into another under the symmetry operations of the group. The next thing to do is to generate the cell itself. And so we've got 4 calcs that we're going to get out. Okay. The first one we'll look at is AG. What you then do is multiply your transformed orbitals by the character of that symmetry. So this is totally symmetric. That's what we're going to get. Right? Everything's a 1. And so we can generate an orbital, a calc. And let's call it psi, as if it were a solution to the wave function of the molecule, which it is. And our symmetry is AG. What is that comprised of in terms of atomic orbitals? Well, you multiply these together and add up what you get. So what we're going to get is that this wave function is the sum of sigma 1 plus sigma 3 plus sigma 2 plus sigma 4 plus sigma 3 plus sigma 1 sigma 4 plus sigma 2. 1 times each of those. You add them together. And so what that becomes when you add like terms together, right? This is the variable A, that's the variable B, C, D, etc. Is you get 2 sigma 1 plus 2 sigma 2 plus 2 sigma 3 plus 2 sigma 4. Because there's 2 of them that are positive. Okay. That's your totally symmetric representation. So then let's look at what happens with the other ones. So let me rewrite this over here. That's our first calc. Now there's one more thing we have to do when we're done. But we'll get to that at the end here. Again, you only have to do the projection part 1 time under this symmetry. But you're going to multiply that now by this second calc, which has B1G symmetry. And so the characters for that are 1, 1, minus 1, minus 1. 1, 1, minus 1, minus 1. I read that directly off the character table. And so we can generate psi B1G, and that's going to be equal to 1 times sigma 1 is sigma 1. 1 times sigma 3 is sigma 3. But now look at this. Minus sigma 2 because that's a negative sign. So negative sign here and negative sign here, we're going to get negative coefficients for those 2 orbitals. Likewise over here, right, those are negative signs there. So if we sum that up over here for psi B1G, what we get is 2 sigma 1. You see that? Plus, I'll keep them in order, minus 2 sigma 2 plus 2 sigma 3 minus 2 sigma 4. So another calc with different symmetry. Okay? You can sort of see how this goes. Next, we're going to do B2U. which is one minus one, one minus one minus one, one minus one, one. Multiplying that out, right? Same type of thing as before. That becomes 2 sigma 1 plus 2 sigma 2 minus 2 sigma 3 minus 2 sigma 4. And the last one, B3U there's our characters. And so that gives us this. And so note, these four things, which are now our four cells, are unique. And they have to be. If you have two of them are the same, that isn't wrong. So the signs are different throughout. So once we have that then, here's our four cells. 1, 2, 3, 4. Don't need that anymore. What's the last thing to do? The cells have to be normalized. And so we have to normalize these wave functions. Which may sound daunting if you've had physical chemistry before, but believe me, it's not that difficult to do. There's two steps. So we want to normalize. First step, multiply by L over H. L is the order of the group. And what is L? We haven't seen that before. That's the dimension of your gamma irreducible. So when we normalize any one of these four, since all of those are one-dimensional, they have an identity of 1, the L is always going to be 1. Now if you had two-dimensional things in this, which we don't, L over H would be 2 over 8 or 1/4. And so your first thing here for all four of these when you normalize them is going to be 1/8. That's step 1. Step 2 is divide by the square root of the sum of the squares of the coefficients. Step 2, divide by the square root of the sum of the squares of the coefficients. So let's do that. Isn't there Cartesian coordinates anymore? We're done with this. So let's normalize. How about we'll start with B1G. You multiply the whole thing by L over H. And so what we're going to do is multiply B1G by 1/8. So 1/8 times 2 sigma 1 minus 2 sigma 2 plus 2 sigma 3 minus 2 sigma 4. Okay. And so that's step 1. If I go and follow that through, what do I get? 1/4 sigma 1 minus 1/4 sigma 2 plus 1/4 sigma 3 minus 1/4 sigma 4. Because you have 2 over 8, that's 1 over 4. And so that's step 1. And now, you divide by the square root of the sum of the squares of the coefficient. So, for step 2, we're going to take the square root of the sum of 1/4 squared plus negative 1/4 squared plus 1/4 squared plus negative 1/4 squared. Right? So those are the coefficients. 1/4, negative 1/4, 1/4, negative 1/4. We're going to square all those and take the square root. And when you do, you're going to find that that is the square root of 1/4. This gives us 4/16, which is 1/4. Take the square root of that. That's 1/2. So the normalized wave function you're going to divide this guy each of them by 1/2. So what do we get out of there? Remember this from 5th grade, something like that? A over B over C over D. That gives you 2/4 sigma 1, 2/4 sigma 2 minus 2/4 sigma 3, and 2/4 sigma 4. So our normalized wave function now, if I reduce that, it's 1/2. If I factor out 1/2, this is the way you want to write it at the end. There's your normalized wave function for B1G. And the rest of it follows through. You do the same 2 steps that you did before. All right, so if we're going to normalize, and I'll just show you one of these, because what's going to happen right, is because of the way the coefficients are. This is what you're going to get at the end of that too. Let's normalize A1G. So L over H is 1 over 8, right? The dimension of A, G is 1. So that's the step 1 of the normalization process. That translates to 2 over 8 or 1 over 4. Sigma 1, 3, 4. If we divide that by the square root of the sums of the squares of the coefficients, they're all positive 1/4. And so we're going to get the same thing out as we did before. And so this is 1/2. And so we're going to divide all these by 1/2. And at the end, coefficients become 1/2 sigma 1, 1/2 sigma 2, 1/2 sigma 3, and 1/2 sigma 4, like that. And so if we factor out the 1/2, now you're normalized there. And it's the same process as we just did for the other two. So without going through every single little step there, right, it's going to be 1/2 times whatever with the signs. And so the normalized V2U is 1/2 sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. And for B3U, it's those. Now you've done the projection operator method to generate your 4 calcs, which are now normalized. And so, finally, what do we do with this? Well, you can draw pictures for them. The coefficients in front of all these are 1/2. And what that means is the size of the atomic orbital that's on there is going to be the same. So everyone is going to contribute the same amount to the calc. So what does this look like then if we draw pictures? So I'm going to represent, instead of having individual hydrogen atoms on there, represent these as spheres or circles because it's 2-dimensional. Right? All of the same size. Pretend that one's the same size as everybody else. What signs do these have? They're all positive. So because the coefficients in front of each individual atomic orbital are the same, the contributions, the sizes of the 4 parts are all the same. And so this is a picture of psi AG. I'm keeping this consistent with my numbering scheme up here as well. What would this one look like? B2G. Or this is 1, 2, 3, and 4. I have a positive sign in front of sigma 1. I have a negative sign in front of number 2, positive sign in number 3, and negative sign in number 4. And so what you're seeing there is the wave function is changing sign as we rotate the molecule, but it's symmetric with respect to the inversion center. Hence the Garada label. Right, this one's totally symmetric, but this one is not going to change sign at the inversion center, which is here. That should not be the case for B2U. And so I'll draw that over here. Notice that we have positive sign in 1 and 2, and a negative sign in 3 and 4. And that changes sign with the inversion center, hence Ungarada. And finally, this last one. Also changes sign with respect to that. And so this is side B1G, B2U, and B3. And that is how one generates cells. Now, it can get more complicated than this when you have more symmetric molecules, when you have p orbitals involved, that kind of stuff. And so we'll take a look at that in the next virtual lecture. But if you're wondering what I might expect you to do on the exam, this is what I would expect you to be able to do. I would like you to come up and write formulas like this for your cells, and potentially draw me simple cartoon pictures like that. Okay, so we will get back to this next time. So we're at about 50 minutes here. That's enough probably for today. Check out the next lecture at your leisure.